Have you ever gazed at the night sky and wondered about your own origins? The profound truth is that we are all children of the stars, quite literally. Every single atom that makes up your body, from the calcium in your bones to the iron in your blood, was forged in the heart of a star billions of years ago. This cosmic connection makes us not just observers of the universe, but direct products of its most magnificent processes. When you look in the mirror, you're actually seeing the results of stellar alchemy, the carbon that forms the basis of your DNA, the nitrogen in your muscles, the oxygen you breathe. All these elements were created through nuclear fusion within ancient stars that lived and died long before our solar system even existed. Through a process that spans billions of years, these stellar furnaces crafted the building blocks of life itself, scattering them across the cosmos through spectacular stellar explosions. Today, we embark on an extraordinary journey that will take us through the complete life cycle of a star. We'll witness their humble beginnings in vast cosmic clouds, follow their evolution through their steady adult lives, and ultimately observe their often dramatic endings. Some stars end their lives quietly, slowly fading away like cosmic embers, while others go out in magnificent explosions that seed the universe with new elements. Others still collapse into mysterious objects that challenge our understanding of physics itself. This stellar story is also our story. By understanding how stars live and die, we gain insight into our own cosmic heritage. These celestial beings are not just distant points of light in our night sky. They are the architects of the very matter that makes up our world. Every breath you take, every step you walk, every thought you think is made possible by elements that were once part of a star. In the coming minutes, we'll unravel the intricate processes that govern stellar life, from the delicate balance of forces that keep stars shining for millions or billions of years, to the incredible transformations they undergo in their final moments. We'll explore how different types of stars meet different fates, and how these various stellar endings contribute to the ongoing cycle of cosmic evolution. This journey through the life and death of stars is more than just a scientific exploration. It's the story of our cosmic ancestry, a tale that connects each of us to the vast and ancient universe in which we live. It's a reminder that when we study the stars, we're also studying our own origins, written in the language of light and gravity across the cosmic depths. Our journey into stellar formation begins in one of the most remarkable structures in our galaxy, a giant molecular cloud. These cosmic nurseries are truly colossal in scale. Picture a dark, cold expanse of gas and dust stretching across hundreds, sometimes thousands of light years. To put this into perspective, if our entire solar system were the size of a coin, these clouds would be as large as an entire city. They drift through the darkness of space like celestial phantoms, containing primarily hydrogen and helium, the most abundant elements in the universe. Within these vast cosmic clouds, an intricate molecular ballet unfolds. Hydrogen molecules pirouette through space, while helium atoms weave between them in an eternal cosmic dance. The temperature in these clouds is astonishingly cold, often just a few degrees above absolute zero, making them some of the coldest natural places in the universe. This extreme cold is crucial for star formation, as it allows gravity to gradually overcome the natural tendency of gases to expand and disperse. The transformation from a peaceful molecular cloud to a stellar nursery requires a cosmic catalyst. Nature provides several possibilities for this dramatic change. Sometimes the shock wave from a nearby supernova explosion, the spectacular death of a massive star, ripples through the cloud, compressing portions of it. In other cases, the spiral arms of our galaxy create density waves that sweep through these clouds like cosmic tsunamis, triggering the collapse of the gas. Even the simple passage of our galaxy's natural density waves can provide enough disturbance to begin this process. Once disturbed, gravity takes center stage in this cosmic performance. As the cloud begins to collapse under its own weight, it fragments into smaller clumps. Each of these clumps continues to contract, growing denser and warmer. This process is similar to what happens when you squeeze a bicycle pump. The gas inside becomes more compressed and heats up. But in space, this process happens on an unimaginably grand scale. The collapse of these cosmic clouds isn't a rapid process. It occurs over an almost unimaginable time span. From the initial disturbance to the birth of a new star, the process can take hundreds of thousands or even millions of years. During this time, the cloud continues its gradual collapse, spinning faster as it shrinks, just like an ice skater who pulls in their arms to spin more quickly. This spinning motion causes the cloud to flatten into a disk, setting the stage for one of nature's most spectacular shows, the birth of a new star. What makes this process even more fascinating is that we can observe different stages of star formation happening simultaneously in different parts of these stellar nurseries. While some regions of the cloud are just beginning to collapse, others might be further along in their journey to becoming stars. This makes these cosmic nurseries similar to actual human nurseries, where you might find infants at different stages of development, all growing and changing at their own pace. The timeline for star formation varies dramatically depending on the mass of the collapsing cloud and other environmental factors. Some stars might form relatively quickly, in as little as 100,000 years, while others might take several million years to fully develop. This cosmic gestation period is one of nature's most patient processes, showcasing how the universe operates on timescales that dwarf human experience. Through modern telescopes and sophisticated instruments, we can witness these stellar nurseries in unprecedented detail, observing the very processes that created our own sun billions of years ago. Each new observation helps us better understand our own cosmic origins and the incredible mechanisms that continue to bring new stars into existence throughout the universe. As the cloud continues its inexorable collapse, a truly remarkable transformation begins in its center. Within this increasingly dense core, the laws of physics orchestrate an extraordinary sequence of events that will culminate in the birth of a new star. The gravitational collapse generates immense heat and pressure, creating conditions that exist nowhere else in nature except in the hearts of other stars. The temperature and pressure rise dramatically in the central region of the collapsing cloud. To grasp the magnitude of these conditions, consider that the pressure in this stellar core becomes millions of times greater than Earth's atmospheric pressure at sea level. This extreme compression forces atoms closer together than they would ever be under normal conditions, setting the stage for the most important process in stellar evolution. As the temperature climbs higher and higher, the core becomes a cosmic pressure cooker. When it reaches approximately 15 million degrees Celsius, something extraordinary occurs. This temperature, which is roughly 1,000 times hotter than the sun's surface, marks a crucial threshold. At this point, atomic nuclei, primarily hydrogen, have enough energy to overcome their natural electromagnetic repulsion and get close enough for the strong nuclear force to take over. This is the moment when nuclear fusion ignites. Hydrogen nuclei begin to fuse together to form helium, releasing enormous amounts of energy in the process. This fusion reaction is the same process that powers hydrogen bombs, but in a star, it occurs in a controlled, sustained manner. The initiation of fusion marks the true birth of a star, a moment when the object transitions from a protostar to a main sequence star. The onset of fusion creates a perfect cosmic balance. The outward pressure generated by nuclear fusion finally becomes strong enough to counteract the inward pull of gravity. This equilibrium, known as hydrostatic equilibrium, will maintain the star's stability for millions or billions of years, depending on its mass. The star announces its birth to the cosmos by clearing away its surrounding envelope of dust and gas, revealing its bright surface for the first time. This stellar birth process produces more than just light and heat. The fusion reactions in the star's core begin creating heavier elements from lighter ones, a process called nucleosynthesis. This is how stars serve as cosmic factories, gradually creating the building blocks necessary for planets, moons, and eventually, life itself. Every atom of carbon in our bodies was once forged in the heart of a star through this very process. The newly born star's characteristics, including its color, brightness, and lifetime, are largely determined by its mass. More massive stars burn brighter and hotter but live shorter lives, while less massive stars burn steadily at lower temperatures for billions of years. Our own Sun, a medium-sized star, has been steadily fusing hydrogen into helium for about 4.6 billion years, and will continue to do so for another 5 billion years. This birth process is happening right now in countless locations throughout our galaxy and the universe. Every time we look at a nebula like the famous Orion Nebula, we're watching this stellar birth process in action, witnessing the same sequence of events that gave birth to our own Sun billions of years ago. It's a testament to the continuing creativity of our universe, as new stars are born while older ones reach the end of their lives, maintaining the great cosmic cycle of stellar evolution. Once a star enters its main sequence phase, it begins what astronomers often call its adult life, a period of remarkable stability that can last for billions of years. During this phase, the star exists in a state of perfect equilibrium, maintaining a delicate balance between two immense opposing forces, the crushing inward pull of gravity and the explosive outward push of nuclear fusion. This equilibrium, known as hydrostatic equilibrium, is one of nature's most impressive demonstrations of cosmic balance. Gravity, an ever-present force that attempts to compress the star toward its center, works tirelessly to collapse the stellar material inward. Counteracting this is the immense pressure generated by nuclear fusion in the star's core, which creates an outward push through radiation pressure and the movement of energy from the center toward the surface. The stability of this phase is truly remarkable when you consider the titanic forces involved. In our Sun, for example, the core pressure is around 265 billion times Earth's atmospheric pressure at sea level. The temperature in the core maintains a steady 15 million degrees Celsius, while the surface stays at a relatively cool 5,500 degrees Celsius. This temperature gradient allows energy to flow steadily from the core to the surface, where it radiates into space as light and heat. During this stable period, the star's core acts as a highly efficient nuclear fusion reactor. Hydrogen atoms combine to form helium through a process called the proton-proton chain reaction. This process converts about 600 million tons of hydrogen into helium every second in our Sun alone. Despite this enormous rate of fuel consumption, stars are so massive that this process can continue for millions or billions of years. The length of a star's main sequence life depends primarily on its mass. More massive stars burn through their fuel much more quickly, leading to shorter lifespans. For instance, a star 10 times more massive than our Sun might only live for a few million years, while a star with half the Sun's mass could continue burning for over 80 billion years. Our Sun, being a medium-sized star, will spend about 10 billion years in its main sequence phase. During this stable period, stars don't just sit quietly in space. They rotate, often at different rates at their equators versus their poles, creating complex magnetic fields. These magnetic fields can produce spectacular phenomena like sunspots, solar flares, and coronal mass ejections. The star's surface can be a place of intense activity, with convection cells bringing hot material up from the interior and cooler material sinking back down, creating patterns similar to boiling water. Stars, also experience subtle changes throughout their main sequence life. As hydrogen fusion continues in the core, the proportion of helium gradually increases. This slowly changes the core's composition and temperature, causing the star to become slightly brighter and larger over time. Our Sun, for instance, is about 30% brighter today than when it first entered the main sequence 4.6 billion years ago. This stable phase represents the majority of a star's life, but it's not permanent. Eventually, the hydrogen fuel in the core begins to run low, and the star must face significant changes. The exhaustion of core hydrogen marks the end of the main sequence phase and the beginning of the star's senior years, leading to a series of dramatic transformations that will ultimately determine its final fate. The main sequence phase, despite its stability, is a crucial period in stellar evolution. It's during this time that stars provide the steady energy output necessary for planetary systems to develop and, in some cases, for life to emerge and evolve on those planets. Our own civilization exists because our Sun has been unwavering in its energy output for billions of years, providing the consistent conditions necessary for life as we know it to develop and thrive on Earth. Nothing in the universe lasts forever, not even the mighty stars that illuminate our cosmos. As a star exhausts its nuclear fuel, it begins its final chapter, a story that can end in several fascinating ways. The star's initial mass plays the crucial role in determining its ultimate fate, much like how our genes influence our life path. Let's explore these three possible endings, each more dramatic than the last. For stars like our Sun, and those up to about 8 times its mass, the journey ends as a white dwarf. This process begins when the star exhausts its core hydrogen fuel. The core contracts and heats up, causing the outer layers to expand dramatically, transforming the star into a red giant. During this phase, the star's outer layers glow with a distinctive reddish hue, and its size swells enormously. In our Sun's case, it will eventually engulf Mercury and Venus, and possibly Earth. As the red giant phase progresses, the star begins to pulsate, shedding its outer layers into space in a spectacular display called a planetary nebula. What remains is the exposed core, a white dwarf. These remnants, about the size of Earth but containing the mass of a star, are incredibly dense. A teaspoon of white dwarf material would weigh several tons. These cosmic embers will slowly cool and fade over billions of years, becoming dimmer and dimmer until they eventually become black dwarfs, though the universe isn't old enough for any white dwarfs to have reached this state yet. For more massive stars, between roughly 8 and 20 times the mass of our Sun, the ending is far more dramatic. These stars experience a violent death through a supernova explosion, leaving behind a neutron star. As these stars run out of fuel, they undergo a rapid collapse. The immense gravitational forces compress the core so intensely that electrons are forced into atomic nuclei, combining with protons to form neutrons. The collapse is halted only when the neutrons are packed as tightly as possible, creating an object of unimaginable density. A neutron star, though only about 20 kilometers in diameter, contains more mass than our Sun. The density is so extreme that a sugar cube-sized portion of neutron star material would weigh as much as all of humanity. These cosmic objects spin rapidly, sometimes hundreds of times per second, and possess incredibly strong magnetic fields. Some neutron stars, known as pulsars, beam radiation from their magnetic poles like cosmic lighthouses, providing astronomers with precise timing mechanisms in space. For the most massive stars in our universe, those with more than about 20 times the mass of our Sun, the final chapter is written in darkness. When these stellar giants exhaust their fuel, the gravitational collapse is so powerful that nothing can stop it, not even the strong nuclear force that holds atomic nuclei together. The star's core collapses into a point of infinite density called a singularity, creating a black hole, an object so dense that not even light can escape its gravitational pull. The formation of a black hole is marked by a boundary called the event horizon, a point of no return beyond which nothing that enters can ever escape. These cosmic monsters continue to grow by consuming nearby matter, including gas, dust, and even entire stars. The largest black holes, found at the centers of galaxies, can contain the mass of billions of suns. Our own Milky Way harbors such a supermassive black hole at its center, quietly influencing the motion of stars and gas around it. These different stellar endings play crucial roles in the cosmic cycle of element creation and distribution. Supernova explosions, in particular, are responsible for creating and dispersing many of the heavy elements essential for life, including iron, gold, and uranium. The materials ejected from dying stars eventually become part of new stars, planets, and potentially life itself, making stellar deaths a vital part of cosmic evolution. Understanding these stellar endings isn't just about satisfying scientific curiosity. These processes have profound implications for our understanding of physics, the evolution of galaxies, and our own existence. Every atom of calcium in our bones and iron in our blood was forged in the heart of a star and scattered across space when that star died. We are, quite literally, made of stardust, the legacy of stars that died billions of years ago to provide the building blocks of life as we know it. As we conclude our cosmic journey through the life cycles of stars, we find ourselves with a deeper appreciation for these celestial beacons that illuminate our night sky. Each point of light we see above tells its own unique story, participating in an eternal cosmic dance that began billions of years ago and continues into the distant future. Some of these stellar companions are just beginning their journey, condensing from vast clouds of gas and dust, while others are approaching their spectacular finales. The next time you gaze upward on a clear night, remember that you're not just seeing static points of light, but rather witnessing different chapters in an epic cosmic story unfolding before your eyes. That bluish star might be a young, massive star burning through its fuel at an incredible rate, destined to end its life in a spectacular supernova. That reddish star could be a giant nearing its final stages, preparing to shed its outer layers into space. Each star represents a different moment in stellar evolution, a different verse in the universe's grand poem. Our exploration of stellar life cycles reveals something profound about our own existence. The iron in our blood, the calcium in our bones, the carbon in our cells, all these elements were forged in the hearts of stars that lived and died before our sun was born. We are, in the most literal sense, children of the stars, carrying within our bodies the atomic legacy of countless stellar generations. This connection to the cosmos isn't just poetic, it's a scientific reality that binds us to the universe in the most fundamental way. Every breath we take, every move we make, involves atoms that were once part of ancient stars. The gold in our jewelry, the uranium that powers nuclear plants, the heavy elements that make up our technology, all were created in the final moments of dying stars, scattered across space to become part of new stellar systems, and eventually, part of us. Understanding stellar evolution helps us grasp our place in the cosmic timeline. We exist in a universe that has been enriched by generations of stars, each contributing to the abundance of elements necessary for life as we know it. This process continues today, with stars being born and dying throughout our galaxy and across the cosmos, maintaining the great cycle of stellar evolution that makes our existence possible. The story of stars is also a testament to the power of human curiosity and scientific endeavor. Through careful observation, mathematical analysis, and technological innovation, we've managed to decode these cosmic processes occurring light years away. We've learned to read the light from distant stars like pages in a book, understanding their composition, age, and eventual fate through the careful analysis of their spectral signatures. As we end our journey through stellar evolution, we're reminded that our understanding of the cosmos continues to evolve. New telescopes, both on Earth and in space, reveal previously hidden details about stellar birth, life, and death. Each new discovery adds another piece to the cosmic puzzle, helping us better understand our stellar neighbors and our own cosmic heritage. The stars above us hold many more secrets waiting to be discovered. They remind us that we are part of something vastly larger than ourselves, a cosmic drama that has been playing out for billions of years and will continue long after we're gone. They challenge us to look up, to wonder, and to explore the magnificent universe that surrounds us. This marks the end of our stellar journey, but it's really just the beginning of a greater understanding. The universe is filled with countless other mysteries waiting to be explored, from the enigmatic black holes that lurk in galactic centers to the nature of dark matter and dark energy that shape our cosmos. Each discovery opens new questions, leading us further into the cosmic unknown, reminding us that our quest for knowledge is as endless as the stars themselves. As we prepare to delve into new cosmic mysteries in future explorations, remember that every scientific journey begins with curiosity. The same curiosity that first made our ancestors look up at the night sky and wonder about those distant points of light. The stars continue to inspire this curiosity, guiding us toward new discoveries and a deeper understanding of our place in the vast cosmic ocean.